So while they're sorting out the last little bit of detail there, let me just give you some background on why we agreed to do this. This came out of an email conversation that Alex started, as many interesting conversations do, with Alex saying, hey, what about this? And he raised the question of, well, what do we mean by interesting mathematics? And he proposed that one way to try to understand it one way to try to get at interestingness was to look at the artifacts that we have, in particular formalized mathematics, right? So there are these very large corpora of formalized mathematics, Mizar being probably the longest running and most stable example of that, which has been running for about 40 years. It's a project that's centered mainly around Poland and has a pretty impressive, sizable chunk of 19th and 20th century mathematics written down and formalized and checked by computer, and it's all working correctly. And there's even a journal in which you can publish proofs in Mizar. In fact, if you write a paper for that journal, I think you're required to write a version of your proofs in Mizar. You can write in English, but you have to also do the computer checkable thing. So Alex's idea was, well, one thing we could do is to query these big corpora and try to figure out what's interesting by virtue of what's in the corpora. Like what parts are there, what parts are being used by other people, what is being referred to by other human beings in terms of this big artifact that we have. So that was kind of his initial gambit in this email. And I wrote back, having just been to a dinosaur dig in Montana just a few weeks earlier, said, well, hang on. In my conversations with paleontologists, they pointed out to me something kind of interesting about paleontology. Namely, we know a whole lot about riparian dinosaurs and dinosaurs that lived near shores. And we know almost nothing about mountain dinosaurs and savanna dinosaurs and desert dinosaurs. And the only reason that's true is that the artifacts aren't there. The fossil record is because they got trapped in mud. And if they weren't hanging around in muddy spots, then they didn't get trapped. So pretty much what paleontology knows about is a really narrow sliver of the fauna that actually existed 65 million years ago, right? So that was my rejoinder to Alex, is that maybe Mizar and formalized mathematics is more like a fossil record than we would want to admit. And then that might not tell us about what's interesting intrinsically, but it might simply be what's interesting because it's what we can get our hands on, which is what paleontology is. What's interesting in paleontology is what they can find. And that's not wrong, right? Paleontology is active, interesting science. But I think if we think what we're doing is looking at something that's an actual record of mathematics, when we look at formal mathematics, we might not be right about that. We might be looking at something more analogous to a fossil record than anything else. So that was sort of the way the conversation went. And then Marco said, hey, let's get this community together and talk about this question of what is interesting mathematics and what makes mathematics interesting. And also, is there a way for us to think about that from the point of view of machine learning and things like that? Like, can we use machine learning techniques, which was Alex's original idea, to try to get at these admittedly sort of proxies for actually being interesting by looking at what we see in the record, which I will continue to want to call a fossil record, but that's just me. Anyway. And I think you kind of agreed that, yeah, that might be an interesting analogy. And we both did agree that doesn't mean it's bad science, right? Just because you're looking where the things are, that doesn't mean you're missing something. So anyway, that's just by way of background of how we got here. And maybe you want to say something else about that.
Yeah, so we had a meeting this morning at 10 a.m. with some students and already had a good discussion. So probably it would be good also to have this just as a discussion. Let me maybe just say a few more words. I wrote down some points here, also partly from this morning. So like one thing is that this could be a really interdisciplinary project, right? So obviously it's about mathematics, and I'm a mathematician, but I also work in software engineering and have an interest in data science. So this is also a data science project, right? Because we have these proofs, these formalized proofs are just data, and then we can do some things with them. It's a software engineering project. It's about AI in at least two different ways, right? So we use algorithms, artificial intelligence to create these archives of formal proofs, which we are going to study, and then we are going to use AI to study this kind of data. And then I think there are a lot of philosophical questions as well. And yeah, I've been a big fan of MPP and also like what Marco and Drew set up here. And so that's another reason I'm actually looking for topics in the intersection of software engineering and philosophy. And I think there could be actually quite a lot of things to do. There are interesting philosophical questions that can be re-examined from the point of view of software engineering. So we can write software that is testing or that provides a perspective on philosophical questions. And I think this could be an example here, like, so what is interesting in mathematics, right? What is interestingness in mathematics? Is a question that actually has been studied in philosophy. I did a little bit of research over the last week on that. So I found books and papers on that topic. Also, Patrick actually helped me. You had a lot of good suggestions. So it was really reassuring to see that this has been a discussion in philosophy. So I'm not just making that up. And yeah, so it's great to see lots of friends and colleagues from different areas here. So I hope we can get something interdisciplinary going on this. So the starting point is that more and more mathematics is machine generated. And I think that we have to find kind of at least an attitude towards it, right? So how, as mathematicians, we are going to deal with machine generated mathematics? How are we going to use software in the way we are doing math every day?
So, sorry. When you say machine generated, do you mean this in a broad sense? Like it could be something
in the broadest possible sense, yeah.
And yeah, anyway, people are going to apply automated techniques in mathematics in probably ways that we aren't even yet anticipating.
It's, also, I want to see actually here mathematics as a metaphor for society in general, right? So like math allows us to ask certain questions in a particular way and also maybe then investigate it using particular means. But the question how we are interacting with AI in the future is a question that is of much broader significance, right? So there are lots of places, workplaces, for example, where they count the number of keyboard strokes you are making per minute, and it's complete surveillance, right? So there's a lot of our daily lives are already basically happening in the matrix, right? And but on the other hand, I think talking about mathematics in particular is that we can stay away from all of these complications and still talk about something interesting that could be relevant more broadly, actually. Yeah.
Can I ask you a question about, so you're right, sometimes one hears that human mathematicians will become superfluous. But I even wonder what that means, because I have a particular view about the activity of mathematics, which is kind of Aristotelian, that it's a terminal good. It's a good in and of itself, right? I'm not studying mathematics. I don't study mathematics because it's useful. It's something else. I don't need it to be instrumental. So, and I think most mathematicians feel that way at some point. We may justify it when we're writing a grant proposal because they're studying math. But the reason I'm interested in it is because it's interesting. It's a terminal good. And so I wonder what it could even mean to say that human mathematicians will become superfluous, because This gets at the question of what we mean by being good in the first, what is being useful. If it's only instrumental usefulness, then we have an infinite regress. And I think that's kind of a challenge, right?
Mm-hmm.
Maybe there's a sense in which human mathematicians would become superfluous, and it is that if you think about the mathematical corpus as what we know about mathematics, so corpus, and then humans could become superfluous if everything that a human can produce, it has been already produced or can be easily produced by a machine.
Right, but I think that just means that mathematics becomes extinguished.
I don't think so. Mathematics could, the corpus could keep
Corpus will keep going, but not mathematics. There's an artifact. There's an artifact, and there's the activity.
Yeah,
And,
mathematics.
and I don't think those are the same things.
But maybe mathematics could keep going by machines. They keep alive the activity. It's not a human activity anymore. But
Would that still be mathematics?
yes,
Interesting question.
If aliens do it, is it mathematics?
Hmm?
If aliens do it, is it mathematics?
yes.
How do you draw the line?
Sure. But they have their
Supposed to be like us,
but
or-
they had their Aristotle. They have their they think about leisure too, right? Leisure in the full sense of leisure, right? Something that you do because, like, you sit down for a meal with somebody. It's not necessarily because you get something. You do
Is
it.
there
Or rituals, or festivals. These are things that we do, not because they're instrumental in some other way. And I really do think of mathematics as being in that category of activity.
Maybe compare it to playing chess. Like anybody plays chess against a world-class chess computer nowadays because it's pointless. But there are chess competitions between humans, and there are chess competitions between computers with humans against each other.
Mm-hmm.
And all of this is still a very active field, and there are lots of people who just enjoy the game of chess, even though we know that every decent computer in the world will be grandmaster.
Also, like if you just would say chess engines generating chess games or computer programs just generating mathematics, that would be kind of pretty pointless because machines don't have to generate mathematics for it to exist. Right? So we can just all of true theorems that you can't possibly write down already exist. So what's the point of having machines writing them down?
But then I think this is a question for Drew, who is arguing that being pointless is out of the scope because mathematics don't have to have any point.
well, maybe it's
The activity itself. Right?
I think you framed the way in this question in a way that lends itself to pessimism too quickly, or to going in this purely like intrinsic style answers.
Mhm.
Right. And one reason for that is like you're looking at for answers in terms of proofs and theorems, and there's certainly interesting questions asked about what makes a proof more interesting than another kind of proof. Right? But it would seem useful to me to step back and think about the kinds of questions that math is answering, right? And we often think that that's something that machines are less good at is asking. Right? They're good at producing answers. They're less good at asking questions. And so, if you wanted to look at a data set, I would think the first place to go would be to look at something, right, like the list of Hilbert questions or the Millennium Prize problem, or like what are the unanswered problems in math, and why do we think that some unanswered problems are more interesting than other unanswered
Can I
problems?
just follow up on that? And you don't even have to go to, I think, something so majestic as Hilbert's problems. I mean, how close are we to computers to performing the function of a math advisor to an advisor to a graduate student who needs a research project?
That's a good question.
I mean, how close are computers to actually knowing the field and knowing what is a good question to just devote some time researching?
Right.
It doesn't, I would imagine we're very, very, very far from that.
I think so, but yeah. Patrick, and then you.
Yeah, I think a very interesting thing to think about is like, why do we reprove theorems that have already been proved, right? So it seems like from a strictly sort of, computational standpoint, like, okay, a computer will prove a theorem and then it might be done. But a lot of interesting mathematics, what we deem interesting mathematics, comes about because we have one proof and it's unsatisfactory or weird in a particular way, and then we want to prove it in a different way, right? Like the prime number theorem is a really excellent example. Like, proved it initially using these complex analytic techniques, but those seemed rather far from the, far in content from the initial question, and so then later.
So there's this purity question.
Yeah, I find this very interesting.
Yeah.
But in general, this question of like, why do we reprove things we already know? That seems relevant here.
Yvonne next, and then Dan.
Yeah, I think, I want to go back to the question of how machines do things as opposed to how humans do things.
Okay, so I make sure that.
And I think there are two areas where there is a big difference. One is creativity, and the other one is intuition. And these two dimensions of human activities are very poorly performed by machines. And I argue, and I gave a talk about that actually AI algorithm cannot be creative. And there are some reasons for that. I don't know about intuition, but that's probably even more true with intuition.
There are people who work on analogy.
Yeah, there are some
Yeah.
sort of, but every time you work on creativity or intuition for machines, you have to narrow down the definition of creativity or intuition, which prove my point. If you have to narrow it down, then it means you are only using a sub definition of it. And I think that's where there is really a big difference. And intuition in mathematics obviously is a big thing.
Daniel?
On will mathematicians become superfluous? I'm not sure that is even possible just by the nature that mathematics that works, which is there's like in mathematics, there's a lot of patterns that we see and around us, but we don't know why they happen. And mathematicians will still try to work to understand why they happen. If you look at the field of data science, where machines have clearly overtaken the human ability to process data, there are still human data scientists. The nature of the science has changed to how do we interface and understand these huge piles of linear algebra that we're working with. The same way, I don't think human mathematicians will disappear. The interface between mathematicians and neural networks will become more important. And that is a really hard problem. If you try to publish a paper in a data science journal about I beat ChatGPT at this particular task by the following metric, nobody's going to care unless you have an explanation about why you did it. Whereas again, this is this interface between the humans are understanding how the neural networks work. It's not necessarily that they're replacing the humans, it's just the interface is changing. And at the end, the human has to understand it at the end to use it, right? And that's why we're doing everything, so we can use it. The human has to understand.
That's...
In data science, mathematics is different.
I like your language of terminal
I don't think
good.
that's true
It's
because
like it's a terminal good for us. A machine, it's not a terminal good for machines. They have no reason to do it on their own.
That's what I wonder about.
yeah, and the other thing is that big data is something that a human being cannot make sense of, but an algorithm can. And even if we don't know how it makes sense of the data, we know that it's able to classify it, to do some classification, some pattern recognition. We know that it's able to extract some significant event in the data, even though we wouldn't be able to do it in one lifetime.
That is true to a point. It's the field of data science is kind of becoming more like a science, the proper science, with hypothesis and experiment, because the way that scientists in this field will not work is that they'll have a hypothesis about the nature of a particular problem. They'll create a neural network that has the symmetry of that problem and we'll see if it works. So it's not really that the data scientists are now doing something that implicitly a human cannot understand. They are just now able to use these machines to test the structure of the problem, so to speak. And you have to understand it from a different standpoint. Of course, you can't understand every data point, but you can understand large-scale structure, which was previously invisible to us. That's the good data scientist. The bad data scientists, yeah, they'll just show a transformer at a problem and see if it works. But the good data scientists, they use it.
No, but you're right. If a machine learning algorithm doesn't produce meaning, then we are not interested in it. Even though we might discover later that it was brilliant, but if we don't make sense of it, then we are not interested in it. I agree.
An interesting question is what would an output from a computer have meaning? Like what would be a meaningful output from a machine learning theorem prover? What would be what do we assign meaning?
Interesting.
So there's somebody online who's got a question.
Yes, can you hear me? Oh, I cannot hear you, so I don't know if you can hear me.
Yes, we can hear you.
Okay, yes, so I was thinking on this discussion, essentially two things that are somehow in the background is like the mathematics. I think a question of interestingness is also about interesting to whom, right? So like an application of mathematics is interesting to someone who wants to use mathematics for something, and that could be interesting to them. But like as Drew said in the beginning, if you're just seeing mathematics as an activity, then the interestingness of mathematics to you is something different, right? So, and I think it connects with, I don't know who was saying this, but this idea of why do we want to reprove something, right? Sometimes a proof, we have a proof and we know something is true, but then we have another proof and we understand why something is true, right? So then I think understanding the interestingness depends on the person, I think. So a mathematician might find something interesting in mathematics that someone who is not a mathematician might not care about. So I think at least, and I think this has been in this conversation somehow, or underlying in this conversation somehow. So, so yes, as a mathematician, I would say interesting has to do with understanding something, right? It is not just that I know something is true, but I can understand why it is true, and that really has to do with like a human capacity of explanation, right? The explanation is something I can conceptualize. So this is my comment here.
This morning we were talking about this reproving things, and well, what about reproving the same theorem the same way every semester, which we all do?
Yeah.
And Alex pointed out that every time he teaches the counter-diagonal argument, it's fun, and it's not because you don't know it. It's not about familiarity, but somehow there's this pleasure in conveying it to a new person. And I find that kind of interesting, right? That it's not interesting to him because, or to me, because we're still wondering why the proof works. That's not the case. But there is this pleasure in surprising someone else that you get from doing it. And this is a pleasure you get from music a lot. As a musician, you do. You get the pleasure from playing something for someone that has either never heard it before, or they've never heard your take on it. They've never heard your interpretation of it before. That surprise is actually an important part of interest, at least for us. And I don't know how that, I mean, maybe computers get surprised, I don't know, but.
We speculated about this connection between interestingness in music and interestingness in mathematics. So, and you mentioned that maybe there could be a way.
Yeah, and there is literature about what makes a melody interesting, for example. What's the difference between an uninteresting melody, like Britney Spears, and an interesting melody like John Coltrane?
I take offense. But I think that this is because we are not seeing then mathematics only as a purpose of knowledge, but also as a culture.
Absolutely.
Yeah, that's absolutely
true. Yeah, I believe
that's
that
important.
Strongly. But that doesn't mean that the corpus is not a proxy for finding things, right? It's an important way that we can query this.
Maybe Giselle, did you want to say something?
Yes. Triggered by the analogy with music, perhaps, and then connecting with the comments that the person did online. Interesting is a term that may denote a value, right? And then in this sense, of course, different groups of people will find different things interesting. And so the question itself, like what do mathematicians think is interesting, may be a question of facts that could be solved by empirical research, so sociological research, psychological research, anthropological research, as in let's see what real mathematicians in different areas think it's interesting and not. So there is this factual way of approaching it. But apparently what's going on here in many of our interactions has to do with the value sense, the sense of interesting as a value. And then when it comes, for example, to making the parallel with music, I think other conceptual aspects that could philosophically interest us could come up. Like, for example, take a Britney Spears song. Oh, that's... But then you see someone, there's this...
I'm really sorry I brought up Britney.
No,
I'm already regretting. I am already regretting.
Just don't do it again.
Yeah.
I want to try to make an interesting point with this case, which is Yael Naim is her name. She is an Israeli musician.
Oh, I know
musician.
her.
Yes, and she has a version of "Toxic" by Britney Spears on the piano. That is fabulous. You can. It takes a while. It takes a while for you to figure out that it is the song, you know. It's only when it comes to the chorus that you see, oh, it's a taste of you. It's beautiful with the piano. And then again, well, it's the same song, but it's presented in another way. It's the same old diagonal proof. It's the same old Pythagorean thing, but it is presented in a new way because in a new context.
Yeah. So again, surprise.
Right, and then it will be surprising depending on the context. I don't want to bring relativism and say it's all relative, but I want to say that when we take interesting as a term denoting value, then of course it will depend on the group, it will depend on the context. And if the context is pedagogical, for example, right, different presentations of a proof may be more interesting than others, given the audience, if you are presenting a proof to fourth graders, to postgraduate students, whatever, right? So this is my comment in the end, is just to say, I think there are so many levels of conceptual distinctions that could help us here. So
and actually,
just wanted,
Patrick and you kind of put together a list of ways that we might think about what interesting means. And Patrick was really helpful in compiling this. And it's quite clearly not exhaustive, but it's a place to get started.
Is that okay, Patrick?
Yeah.
I put this up. Yeah. So I thought this was kind of helpful. I don't know whether you can see that actually.
Can everybody see? That looks like that might be okay. Yeah, that's the list that we
It's
have.
already quite a long list, and it might be possible to even add stuff to it.
I'm sure,
Yeah. Do you want to say something about how you thought about compiling this?
Yeah. So I wasn't thinking of relative to a person, but of course that is a way to think. I think something that is very interesting about interestingness in mathematics is that even though there are many different ways you can think about it, it seems that there is still a surprising amount of agreement, maybe. And so these are just some sort of common theoretical virtues that you might appeal to in philosophy that have been around, especially in philosophy of science, actually for a very long time. And so that's kind of how I came up with these. But there's literature on simplicity, unification, this notion of surprise. But I put this in terms of the content of the theorem. Ostensibly it's about X, but you prove it using Y. That's interesting in some way. Yeah, I mean, this notion of beauty comes up a lot. This one I find that seems too wild and chaotic to me. I don't know if there's enough structure to be had there. Explanation, fruitfulness.
Except that the reports of beauty from mathematicians are pretty consistent.
There is a weird amount of consistency.
So something's going on there, but I don't know what it is.
I don't know. Yeah, there's something
Let's
about
all the other
me.
stuff that can't be formalized.
Yeah. I mean, some of this can't be. I mean,
We use math to study beauty in other domains.
That is, it's true.
It's true too.
Just a question about the list. It's interesting. You're saying the proof is simple. The proof is unificatory.
I thought about it in terms of
Not propositions are.
I say something about this later because you might ask questions about, okay, what about conjectures? I mean, yeah, like asking questions versus.
So I
just
mean,
proving
not that
things.
this is, you could have two lists, I guess.
Yeah, I think you could,
Yeah,
many
and-
lists, but I just focused on proof, but yeah.
And John mentioned that a little while ago. What about conjectures, some of which sort of people keep coming back to, and others really care, right? So which ones, why is that? They're both still conjectures. You just don't know them, but like the Collatz conjectures, mostly people don't care about. Most people don't care about, but a few people really care about it. Right? So I think that's kind of an interesting problem. Conjectures should play a role in what we think is interesting.
I mean, the conjectures that drive research.
Yeah.
Yeah. It can drive research at so many levels, at just also a very modest level. I mean, but that's, again, I think that's something go back to the question of replacing mathematicians with computers. It doesn't seem like that's something right.
Like a conjecture just literally makes research happen.
Right,
Like
no, right.
Yeah, at the low level, they certainly
As to
do.
what are people looking at to try to prove it? And I don't think, machines are.
Kai, you will.
Yeah, I have several related
And then-
questions. So you were talking about teaching the same theorem over again and it being fun. And I was thinking about what makes it fun. And then the related side of this is, can we make a computer do these same things? Can we make it sit down and have tea with its friends? I mean, at what point do we draw the line and say this one is like a human or an alien that you're comfortable calling it does mathematics, and this one over here is a machine that does not do mathematics? So that's a hard line to draw. That's one thing. But the other thing was about fun, and I think maybe that falls kind of under the beautiful category you have in here. And for me, I think the reason that I would have fun teaching a thing is that I think it's clever. It's a neat trick, and I get to show the student the neat trick. And so I wonder if there's a measure of cleverness that is part of it. Maybe that's just another word that means the same thing. I don't know if I'm really adding anything, but that was my thought.
I do agree.
No, sorry.
Go ahead.
Well, yeah, the like cleverness, I feel like you can try to cash that out in terms of other things, maybe on this list, maybe not on the list. Like, this proof is clever because it's simple in the sense that it uses just like two ideas rather than a bunch of other ideas that you could do it in this way. So yeah, I guess it often seems to me that like, yeah, cleverness or beauty, these sort of aesthetic judgments often bottom out in some of these other things if you start to like pull it apart. But that's just, I mean, yeah, again, this is just very initial thoughts.
So I just want to say that Luke has to catch a train at some point, and he looked at a bit of the data this morning, and so he can maybe show us, give us just a glimpse at what you can do with data, right?
Is there anything you want to say about the data? I don't know much about the data set.
Oh yeah, so this the data set is from the Lean math library. And so Lean is one of these kind of archives of formal proofs that is quite popular, maybe the one that is kind of pushed most. And
I think most active.
Yeah.
Being built today. I think that's fair.
And so you have this huge collection of files with definitions and theorems and proofs. And this data is just scraped from this math lib. And then they build a graph from it by looking at each file, and each file, like Lean is also a programming language, so it's a language to write down proofs, but every proof is a program and vice versa. So as it is usual in programming, at the beginning of the file you import other files, right? And then these imports give you a graph. And this graph is not exactly the graph that I had in mind when I came up with this. So I was thinking more of a graph where a theorem links to another theorem if the second theorem is used in the proof of the first one. So I was thinking about is used in the proof of graph, and this is the import graph. So it's a little bit a different graph, but I think one can already kind of get some idea how much fun it can be to just start from the data, right? So far in the discussion, we started from the philosophy, but we can also start from the data. And actually this morning when we met, Luke immediately started to do that and kind of play around with this data. So I think it would be nice to hear from you like kind of what you did.
Sure. Yeah. So we were looking at this. This is just all of the files and all the edges between these. So this is a file, category theory.sites. Pre-topology is going to be these files here, category theory. Yeah, so it's that's living somewhere in here. And when you hover over something, it'll show you all the nodes connected to it, and that just means all the other files that it has some relationship to. And these are the files. These are not sort of the structural links between the theorems or even the foundations of the theory. It's just, but you can glean something about it from that. So this, I did not do this. This is something that Alex and Drew shared this morning. And I started poking around with, modifying the code a little bit. So this is a package by Eric. Sure. This package here, and it's...
Yeah, so he's one of the contributors to Lean, and he has created this data visualization, and then that's kind of what we take as our starting point here.
So I forked it and can play around in here in this code base. Everything's just in this index.html file if anybody else wants to play. There are a couple things I added. One is I threw back in this data point that they get rid of, which is so this is the Lean files. It's a programming language. It's the core init default is every other file depends on this file. And they got rid of that. And it looks quite different, right? So you can get a sense of what happens when you start adding or removing nodes, is that it starts to reveal a little bit about the inner structure and makes this way less complicated. But now if you click on a node, it'll remove it and restructure. So that's what happens when you remove, the one dependency of all the files.
And you only started messing with this morning, right?
Yeah, so it took like 5 minutes to modify the program that we forked from GitHub to make modifications like, oh, what happens if I take out algebra? Right? And then you see suddenly interesting things happen.
So this is algebra. Algebra is all that red. If we take out algebra, we start to see some orphans flying off. And it's so interesting to me what we're losing. Right, so what is this? This is a ring theory ring involution. For some reason, we're losing ring involution when we lose algebra, but not entirely. It's still connected to ring theory, so that's the reason. But I was playing this game of just, let's get rid of model theory. Let's get rid of, and you can just sort of keep playing
Things
this game.
didn't change much when you got rid of them. That's interesting.
Isn't it? So this, and then you see this out here. These are just dependencies. This is the core library of Lean, And so if we get rid of the core, that's not really informative about math.
Can you please take logic out?
Yeah. One moment.
We should take a photo.
But it's not weighted graphs, right? They're just plain linear if there is a dimension.
There we are. Okay,
Then
so
it doesn't mean anything.
get rid of all of this.
Yeah. Well, it's even worse because if you look at the colors, they're colored by alphabet. So, right, the blue things are unrelated to each other mathematically.
Because if you remove logic or algebra, everything will disappear.
You wanted to get rid of logic?
Yeah, just to see how.
There's not too much there.
And then my point is made.
We lose some counterexamples, some erased data.
That's the same spirit. Can you categorize?
Let's get rid of data. I don't know what data.
Look, this is not a grievance session. We're category.
Dominic, this is data. I don't know what it means, but I think it's a lot of what you're concerned with.
Okay.
So we lose a lot when we get rid of data. A lot of order.
This is really satisfying intervention.
Yeah, but that's because data, it isn't what you think it is. Data is actually putting things like lists.
Okay.
Data structures.
So linear algebra.
Yeah.
Representation theory. I don't know how to interpret this exactly. So the orphans fly off. They're telling you something about, you know, sort of what was, you know, it was a child of this, but it remained categorized with something else. So it wasn't deleted with it. So it's sort of residual. So I think that's kind of interesting. Another thing that I was sort of hoping to
Doesn't
look at.
flying off mean that it has no dependencies? It didn't import anything other than the one you just deleted? Is that what that means roughly?
It means that
Yes, pretty
it
much.
was held together with this cluster by that. It was the only, that cluster was the only thing holding that.
Tying it to the rest of it.
Yeah. So one of the things I wanted to look at was, for example, with, I don't know if we can do this with this structure. We might need to refine the graph so that it actually incorporates the, you know, the looks at the logical structure or the lean theorems and tries to look at the dependencies of the theorems. But Peter brought up an example this morning of the parallel postulate and got me thinking that if you look at all the dependencies of the parallel postulate, you get one sort of world of geometry that's really interesting. But it's also sort of, the parallel postulate is so interesting because if you remove it, you get this whole other world and very large world of interesting mathematics. So looking at like bifurcation points is something that I think, you know, if I could click delete parallel postulate and see all of geometry except for like non-Euclidean fall away or some sort of cluster separation. Yeah, so it's pretty satisfying to just watch things fly.
Watch pieces of mathematics fly out.
Yeah, it really is. And if you want to, yeah, so you can play the same game with individual. So if I get rid of Boolean algebras, it's actually kind of important. Can sort of play the same game and see what clusters separate. In general, you wouldn't just get orphans flying off. You could see like what could you remove from this that would separate into two large clusters. That's where I think you're getting at something interesting.
Right.
So I think also what this shows is that algorithms can create new interesting questions to us, right? Or even just making an interface to that. If you have an interface that makes it easy to explore different questions, then these questions may become interesting questions about kind of mathematics as a science or mathematics as a field, and they were just not available to us before.
Oh.
Any other requests? Let's get rid of set theory.
Yes.
I knew there would be some of you out there. Probably a lot of us.
But so that's interesting because if you know anything about the lean library, there's actually quite a, I mean, it's getting better, but there's some duplication in it. So there are certainly theorems that depend in some way on cardinality, for example, but they might not. They might not be formalized in a way that they imported the set theory.
Right. And I think that's sort of what it shows is that if all of mathematics, if like this whole cluster stays together, when we remove set theory, I'm trying to interpret what that means. It's really saying something about, you know, we don't need set. There's another way to do it. The rest of mathematics is sort of holding itself together. And so there's this question of like, when you remove this core default. This is something that every other file depends on. But when you remove it, everything stays together. And that's very interesting to me because it's saying something about, it isn't necessarily the most leaned on packages that are, or the most, the axioms or libraries that are most depended on that are most interesting.
So in a way, if you remove the foundations of mathematics, everything still hangs together.
Yeah.
So we don't need foundations.
But then the
Is that
question
the way
is
to
how?
read it?
Yeah, I think so.
Well, what the
How does it stay?
the clusters, what staying together means is that,
They're using each other.
they're using each other. So
So isn't it the case in your graph that if I have nodes like this, and this is set theory, and I remove it, the graph is still connected, so nobody gets lost.
right.
And I think that's what's happening. So you're removing pieces, but they're also depending on maybe algebra or data or something like that. This is a K-connected graph for some very big K, I think.
And then what's
In other words, the minimum number of nodes, the minimum number of nodes that you could remove to cleave it into two parts.
Mm-hmm.
It is a measure of how densely connected a graph is. Right, and I think this is a very densely connected graph.
So when things stay connected, we don't get a sense of how broken they are, having taken out the one piece, right? Sure, it's still referencing other things, but did you really need that one you took out? And that's not really appearing in this visual.
Yeah, not this. A finer grained version of it would probably do better for us.
Yeah.
Like one that's really telling you this theorem depends on this theorem. These are just file dependencies. And that depends a lot on the humans who decided to chunk them in certain ways.
Yeah. Yeah, because usually there is only one proof for every theorem.
That's actually design decision of Lean, is that they want it to be that way.
Exactly. So,
Right.
But this is not telling us something about mathematics, but about the implementation that they decided on.
Right.
So here's an example where I just removed a bunch of stuff, and down here we have Euclidean geometry. Up here we have topology holding curve geometries. So you can sort of see it depended on how I cut things. You can sort of see the way that playing around with sort of pruning these graphs can show you a little bit about, what we understand about math. I think that's all I have. Anybody have any requests?
But I guess this is telling us that mathematics is more cohesive than we could imagine by looking at how it is divided all over the place. But actually, we are always trying to use techniques from wherever they come. So whatever is, I don't, if I can use some theorem from analysis, why shouldn't I, right? And this is what people do.
And maybe this could give us a way to study the unity of mathematics, right? Because we see a lot of math in one. Yeah, Jonathan.
I think that's also what the people involved in these two big kind of projects, like directed towards achieving something in arithmetic geometry, like based on Scholz et al.'s work, first for the perfectoid spaces, and then for like more recently condensed math. So for both of these like big and like many people projects, they're reporting, okay, we have to formalize a lot of algebra, a lot of topology, a lot of analysis, more on the expected side, but then also a lot of, combinatorics, for the liquid tensor experiment specifically. And so maybe that wasn't, that expected to begin with. I mean, much less than, I don't know, theorem in topological algebra, which is like more, the primary field of application. Exactly.
Yeah.
Giuseppe has a question, so please mute yourself.
Hi, Giuseppe. Go ahead.
Yes. Can you hear me?
Yes.
Yes. Yes. More than a question is just a remark. I mean, I find this clustering very interesting, but this clustering has to do with topics, right? I mean, mathematical theories, algebra versus combinatorics versus, I don't know, information theory and so on. So I would be, as a proof theorist, very much interested in categorizing proofs depending on which kind of inference rules we are using. Are we producing a proof using, I don't know, a case analysis, double negation? Are we using a constructive proof? Are we using, I don't know, this kind of thing? And this is a fundamental, problem in proof theory. How do we categorize proofs? How can we possibly tell apart two different proofs of the very same end sequence, or possibly put them together in the very same basket? And as mathematicians, we pretend to know where to do that, when we should put two different proofs of the very same end sequence in the very same basket. But actually, the techniques that are available, are a kind of hybrid. So there is some intuition there, but also, somehow we already heavily rely on external tools. So, somehow we ask the lambda calculus or the proof nets or the focalized proof sequence to help us to tell apart two different proofs or to put them together. So we are already heavily relying on some kind of machinery that is not necessarily connected to our intuition. So I'm very interested in machine learning and these kind of techniques because this provides more examples on how we can possibly categorize proofs independently from our intuition, and that's I don't know, stuff I can work on as a proof theorist. So I'm super interested in this project exactly because I think it will provide, yes, more insights on how we possibly think of proof, understand proof, categorize proofs, like proofs. Yeah, that's all I want to say. Thanks.
Did you have a question or a comment?
Yes, I need to say first. Yeah, my comment is very short, and it is that this is a very interesting project that Giuseppe is advancing, but I don't think that mathematicians are careful enough to write down in Lean the most effective proof or the proof that requires less effort or anything like that. I think that mathematicians are just going to write whatever proof they can. It doesn't matter if it is by cases, if it is by contradiction or by contraposition, they don't care. I don't think they care that much. So I don't think we can answer the question on how can we classify the proofs, because I don't think that mathematicians are going to be careful enough to write down the best proofs. But Jonathan had also.
I think it's even worse because specifically in Lean, you have these like pretty powerful tactics. So to really know what you would, it's super easy to write down basically like a one-word proof in Lean that would be 10 lines on paper, and that would be on paper kind of, much more, would use probably like much more weaker systems, or like assumptions than just this like, I don't know, steam hammer like tactic. So it's something that even by just looking at the code in a Lean proof, you wouldn't know, because
and steam hammer, by the way, is the name of the tactic in Lean. It basically just means I know this is provable and easily, but I don't feel like doing it. So Lean, find the proof for me. That's more or less what it said.
So maybe if you had some kind of bytecode, yeah, I guess it's either but Lean has
Sledgehammer.
I guess like in Lean you have like ASOP or other kind of tactics, and so like sometimes it's kind of difficult to even really reverse engineer like a Lean proof, like a working Lean proof, just because the tactics, I mean, under the hood, they're doing so much. And I don't know if there's some kind of lower level bytecode like version that tells you a bit better. I guess you have a stack trace and you can kind of see.
And I think there's some people working on
what is going on. But I don't know how difficult it would be to do an actual kind of, I don't know, ordinal or like reverse math analysis on this.
I mean, it doesn't do it for you automatically, but the Marine system underneath it has the full type theoretic term that justifies the proof. So the details, you can even export it and have it checked somewhere else. But this is definitely not the proof that you want to read. So it's just as unreadable as the tactic proof. But it could be amenable to the kind of questions that Giuseppe has, because at least for that particular proof you can answer what does it depend on, what methods is it using, is it constructive or not. The other question would be, is there a different proof that is better? And that's something that computers can figure out, but right now we don't have particularly good tools for that.
Marco.
Yes, I have to say a little bit confused here, because not only I do not understand what is interestedness in mathematics, what he was expecting, but I am not sure to understand what we want to decide to call interesting. Want to decide to call interesting proof, a theorem, a connection, a definition,
That's right.
a way of organizing a theory. So I think that we should begin to decide what is the object in the predicate it is interesting. And then we can decide what interesting would mean. But if we do not decide what we want to call interesting, I think that we will discuss up to tomorrow morning without doing 1 centimeter of progress. And possibly there is not only a decision, a good decision, possible there are different decisions, but we should be clear that according whether we choose one subject rather than another, for example, a result rather than a proof or a definition, possible the sense of interesting can be different.
Yes.
Okay, so this first. Second, what I said this morning, I think that certainly what is for a theorem, for example, to be interesting is possibly largely a subjective question. But what is for a theorem to be interesting if some criteria of interest has been chosen, in many cases could be made objective by research as this one. For example, we can use, as I was saying this morning, we can use an algorithm as a page rank to page rank to identify, to classify interest in a certain sense. So perhaps something that really can be done if we want to approach the way, in an empirical way. But remember that to approach the things in an empirical way does not mean to eliminate not empirical reflection. Empirical research is guided by philosophical reflection. Okay, so if we want to approach the things in an empirical way, possibly we should begin to make a sort of table. One, what we call interesting, theorem, result, definition, etc., etc. And then for any one of them, do we identify different possible criteria of interestedness? And we go to construct the ranking of these different, and then we compare the ranking. And so possibly if we compare the ranking and we discover that in the category of theorem, in any ranking, there is a theorem that appears in the beginning, so possibly it is absolutely interesting, independently of the fact that it is for you or for me. This is the one that came first under all criteria. So I think that an empirical work can be, otherwise it is a very empty discussion. If we want to really to use this corpus and to use these tools to make this research, I think that we should be pluralist. We should be pluralist, but not confused.
Can I make a counterclaim that subjectivity is just local objectivity, and the more globality, like if you ask for consistency globally, you lose less. You just sort of course grading over local interestingness. So you'll lose some. If we only look for like empirically things that are like interesting to you and me, then we lose out on what's interesting to you but not to me.
So what do you say? Subject.
I do not understand the point.
Just have
I understand that.
I do not understand.
Like, you know what's interesting to you. It's locally objective to you.
Oh, I see.
Yeah.
Now, I take your point that, I mean, if this is going to be more than just an interesting afternoon, then we need to do something about that and start thinking about what is the actual object of study. Theorem.
What is the actual object and what are the different senses, and then compare the rankings.
Yeah, and so Patrick has helped us on the second part of that. What are the ways in which we can think about interestingness? But then we still need to think about what are the artifacts that we're considering in the first place. What things
for Patrick, it was taken for granted that what is interesting is proof.
I didn't take it for, I did say later, but yes, I focused on proof. That's right.
Well, but
it's a very good choice, but it's not the only one.
Right, of course.
No, absolutely not. But it is one that mathematicians will oftentimes land on, right? We are interested in. I mean, Erdős was really overt about that. He was interested in the book proofs, and he wanted to know the proofs in the book, not the theorems in the book.
For example, here is one possible criterion. If we want to take interesting the theorem, we can imagine that the most interesting theorem is the theorem that has most proofs. How many proofs has this theorem? Pythagoras theorem. Why is it interesting? Because it has 125,000 proofs. And it's one criterion. Of course, it's not the only one, but here is one. And many of these criteria can be objectively measured. How many proofs are in the corpus of Pythagoras theorem? We can go and count. It's not a question of subjectivity. The result is 25 point.
Right.
And so once we have compared all these different criteria, so perhaps we can have a more precise picture of the situation that does not depend on the fact that you have your taste and my taste. For me, the most interesting thing is Frege definition of real number. But of course, it's
yes, but you're just wrong.
It's a little bit, so to say, provincial.
Yeah. I mean, what do we do next? I mean, I think there's a lot of smart people here, experienced mathematicians.
I made a suggestion that I'm absolutely not capable to implement because I'm not neither a mathematician, not a computer scientist. But I think that I make this suggestion for you to work on.
Just counting the number of theorems?
No. To identify different subject, and for any subject, different senses, and then to try to measure objectively the senses with respect, and then to compare the ranking that we have.
Yeah, because that begins to be a research program.
Exactly.
Yeah, no, I agree with that.
It's sort of a conceptual organization and then could lead to different specific objectives, right? And aims. What will be more empirically informed and what will remain more conceptually driven.
Yeah. There's been some recent, sorry. Who are you pointing?
No,
go ahead.
So it's kind of a bigger thought, though.
Go ahead.
Finish that line.
No.
Well, we talked about attributes or conditions of interestingness, absolutely necessary for the project. But I understand it's the interestingness of mathematics, what counts as interesting in mathematics. And we've left schematic what mathematics is. And even if we all agree in every case on what counts as mathematical question or object or statement, we still talked about the attributes or conditions of what makes something mathematical. It's perhaps a much more difficult question, and perhaps it's on my mind because it's related to my project. But if then we take the attributes of what's interesting and the attributes of what's mathematical, program to be filled out a little.
I think it's also related to your point, Drew, right? So that the data we have is like a bit like the fossil record, right? So there's a lot in mathematics that we'll not find in the data.
Perhaps all the times.
And then connected with what Ben, with the big question that Ben is bringing up is like, are we talking about mathematics like now in the 21st century? Are we considering historical aspects, yes or no? Because that could be another variable, right?
It seems like something suggested by the beginning was that you're also interested in interestingness with computers, like how that will change things.
Mm-hmm. Yeah, because it seems like it will be a moving target. Yeah, there's some recent things. Tim Gowers wrote some stuff, and there's a volume that I sent around to a few people, and I forget the title. Sorry, I'll find it later. It's a book of people writing about narrative in mathematics and the importance of storytelling in good mathematics. And I think that's has something to do with your example of proving the same theorem more than once to different audiences. I mean, a good comedian can tell the same joke over and over again and still enjoys doing it because there's something about that performance that's sort of fun. And the narrative structure is part of what you find appealing. A good story is a good story, and you don't mind telling it over and over again.
An audience sometimes it's like a funny movie, they watch it every year.
Yeah.
Funny person, and they always go to it.
Yeah, and I think we shouldn't discount. This is going against what Marco was saying, but I don't think we can discount the importance of what makes things interesting is that we can tell them as a story. What makes something interesting is that we know that it has a structure that we can tell as a story. There's a narrative structure to some things and not other things. And I think that's really quite important, especially important pedagogically.
Structure. So what is interesting is the net and not the.
Yeah.
That's what you say.
Yeah, I think so. Why? So calculus 1, I wouldn't necessarily always consider this to be interesting, but just bear with me. It has a story. It has a narrative arc. You build it, and the punchline, the point of the story, the denouement of the story, is the fundamental theorem of calculus. And if you don't get to the fundamental theorem of calculus, you feel really disappointed. There's really something missing from that. Maybe you didn't prove the power law, or maybe you didn't do this. That's okay. But if you don't do the fundamental theorem, you have missed an important part of the narrative of that story. And I, at least as an instructor, as a professor, I am mindful of storytelling when I try to teach. I'm unsatisfied when I have to teach a course where there's just a sort of march through unrelated topics. That's no fun. Telling a story is fun.
So I'm not a mathematician. I've studied mathematics a bit, but I'm an economist. And this relates to what you just said and what you also said at the beginning, that math is a terminal good. For me, it's an instrumental good. And I don't just mean that in an applied sense. It's not applicability and instrumentally useful aren't necessarily the same thing. It's transformative, right? I like to learn math, not because I find it interesting. I actually find it a slog most of the time. I'm sorry, I know I'm the minority here. But I change as a person, right? And when you go through Calc 1, you change as a person having gone through that experience. And so, and I think that might be some of the joy that you're experiencing when you're sharing it is, well, yeah, new people are now transforming. And so this is a lot of, at least what I find interesting in mathematics is how do I change and how do other people change? And I look back at things that I found really, really hard 10 years ago and I go, it's so easy. Why? Because I've transformed through all the different processes.
That's the humanity. Basically.
I actually agree with that pretty strongly. I think that like one of the big points of learning math is logic. right? But it's not just logic for the sake of logic. It makes you a more interesting person and all these things. Even if you're never going to use it as a mathematician or you never even find it fun, you develop.
I think this last point brings like again the variety of aspects of what's being talked about here, which is then what Drew is saying and you're saying too, is like there is a strongly performative aspect to the process of teaching and doing mathematics as an activity. But then there's also the corpora, the file, the things that are there as in a stock, right, of information, that of course, and then how they interact. So again, what's interesting, someone could think that it's more interesting to look at the corpora, to look at the stock, to look at what's in the archives and how that information relate aesthetically, but then there's also the dynamic and performative aspects of it. And
Yeah.
so again, just making distinctions that could help us.
But I want to be clear, studying the corpora and studying the artifacts is valuable.
Oh, absolutely.
Even though I'm saying things about performance, narrative, and all this.
Yeah.
And terminal goods, blah blah
I
blah.
agree.
But the fact is that that's where we can find the record of what.
Absolutely.
So
Because these
as long as we're mindful that it is something of a fossilization, it's not right. We're probably missing some things that because we're looking at the.
There are aspects of mathematics, right? So of course they interact and et cetera. Sure.
Okay.
Please, yeah.
Yeah, I guess I just wanted to say like the narrative structure actually indicates to me that like there's really objective phenomena there, right? We're talking about it in this kind of subjectivistic way, but right, like there is just a fact of the matter that like, okay, when you teach Calc 1, like, yeah, if you ignore like something about like power series, okay, maybe that's okay. But yeah, if you don't talk about the fundamental theorem of calculus, you've just done it wrong. Right.
Well, you set up a joke and you didn't tell the punchline.
Right. Yeah.
You don't do that.
Like there is wrong. Yeah. So the fact that we can give this kind of narrative structure to like teaching sort of a historical mathematical subject indicates that there is like real objective phenomena there, and that's why the history of mathematics is so important, because it allows us to kind of sift out like this is what was interesting because this is what produced new mathematics, or this thing was just like a weird like terminal point in mathematics that kind of died.
So
But that is a very good suggestion, because if you ask what is interesting in mathematics, it's very easy. Ask to the only historian here, me.
Hey Marco, I try.
So what's so what's interesting? And do not say Frege is.
I do not say Frege. Wrong. Correct.
So what you said reminded me of a possible use one could make of that research. Like, I mean, in data science also, telling the story is at least as important as the mathematical analysis. So maybe one can develop tools here which give us new possibilities to tell the story of mathematics, or a story in mathematics. And that could be interesting just for teaching itself maybe, but that would be already something valuable to do. Okay?
What I'm going to say is kind of going to change the subject a little bit. So if there was a follow-up question, maybe you should ask it.
Jonathan next?
I was kind of tying to different things. So because when earlier you said how you enjoy like Cantor's diagonalization, telling this, I figured it maybe was also because of the narrative and and sometimes, or like if you tell the story about Gauss adding all the integers from 1 to 100, okay, mathematically it's not complicated by today's standards, but it's it's somehow an interesting narrative, both historically and instrumentally.
Dead mathematician.
And and I was kind of also I had like a similar thought as you, Alex. So like, I mean, if we're kind of building kind of corpora or thinking about different ways of organizing math in like the digital age, we could also think about doing something like this for the history of math, kind of like in a, it would be a different project, but it's also not unrelated, right? So
would you mean following the bibliographic record, or?
Well, not just,
because that's pretty crude, but you should use it.
Yeah, that would be a part of it. guess. But just to understand, I mean, understanding mathematics. So, I mean, we started this discussion by kind of saying, okay, let's understand mathematics or interestingness in mathematics, but also interestingness. It also, so I liked your comment about that. I mean, inherently, it also has like a time component, and some things they stay kind of constantly interesting over time, but some other, like something that has been a problem 500 years ago is maybe not, you know, such an interesting problem today. But then keeping track of how interestingness changed, which maybe is also part of what people are doing when they're studying history of math, that can also be like a, yeah, like a project in itself. That's what I'm saying, and yeah.
I think, related to that, I think it would be interesting to have a distinction between what is interesting and what is fashionable. Because sometimes people do what is fashionable.
So this is not really
like Britney Spears, what I wanted to bring up. Don't do it. No.
So what if we just forget about mathematics for a moment and just say, what is a measure of interestingness? And I would, for me, as a person, I think it's a measure of how much time I spend with my attention on a subject. So just a relative amount of time. And I think that relates to your question about fashion as well. Like if something is fashionable, maybe I'm thinking about it. It's interesting for the moment. Maybe that fades away. Maybe some things have a more sustainable kind of interestingness. So it's really hard to quantify, you know, this for people, but we actually maybe can use a simulacrum. We could use a machine learning algorithm. We could say, okay, prove this theorem for us. And now we can look and see, okay, how much time did it spend, or how many times did it call particular other proofs or theorems along the way? Which ones did it need to use? This isn't exactly interesting, but it's like a measure of attention, kind of. How much attention had to be paid to these things in order, you know, to get to this answer? And that's going to be just using stuff that we already know. That's not going to be what's an interesting new question, but maybe we can get an idea of a measure of interestingness in that way.
There was a mailing thread discussing things about that, and then someone suggested using time as a way of measuring, but then someone else thought, okay, but for example, we spend a lot of time doing dishes, and few people would say that doing dishes is interesting. So maybe time should be, yeah.
I mean, time can be interesting if you pair it with, I think there is a strong connection between interestingness and emotions, and the kind of emotions that you feel as you do it. And maybe we can couple time with the balance of the emotion. Like if I spend a lot of time on something I don't enjoy doing, but I have to do it, it's probably not because I'm interested. But if I spend a lot of time on something I enjoy doing, then there are more chances that it's because I'm interested.
So the product of time
So,
and enjoyment.
so some
something like that.
visual researchers have thought about what you brought up, right? Displaying images and allowing people to spend time on one or the other and measuring what they do. They've used that as a proxy for interestingness, for visually. So there is literature on that.
It's the basis of a lot of studies in cognitive science, or
Right.
developmental psychology with babies.
Exactly.
I was thinking about what you said about narrative and the comment I started off with about kind of thinking about big classical questions that get lots of attention. And it seems like one way to kind of operationalize thinking about this is, right, there's a set of desiderata that you might care about that seem like they're relevant. You have a database of a bunch of proofs. You might find databases of conjectures and other kinds of things. But rather than just brute forcing it, one way to try to find a starting point for things is to use some, right, like you can look at like things that have been awarded, that people have been awarded the Abel Prize for, right, which is, it's not going to track just interestingness, because it also tracks something like importance and fashion and things like that. But that gives you, right, a set of propositions, right? If you're looking at that graph and think, well, what should we start taking out to see if, like, is there anything common to Abel Prize winners that when you take them out, they change graphs in a certain kind of way that other things don't, or they occupy certain positions in the graphs that tells us something about at least the combination of perceived importance and interestingness and influence in the field. And then from that you can maybe generate a set of further testable propositions that you can brute force through the entire kind of.
So you're suggesting this is a sort of first part of experimental design, right?
I mean, I'm partly saying this because I'm teaching a course on the Nobel laureates in economics right now. So this is like the mathematical equivalent of doing something like that. But
so did you do some data analysis with this idea of the Nobel laureates?
no, I consulted my own intuitions about a combination of whose ideas were both accessible and important.
Right.
And interesting.
Yeah.
Any other comments? What am I supposed to say? Comments?
Questions?
Protestations.
Protestations.
So I want to say, like, what is the motivation behind defining interestingness? Because I'm worried that we could get to a place where we start deciding which mathematics are worth doing and which ones are not. Because there are some theorems that I could say are very ugly, but that lead to very beautiful things. So I just, like, what's the motivation behind defining this interestingness?
There are already organizations that decide what kind of mathematics you should be doing in which.
Yeah, or like journals, right? That we're forced. So I don't want.
Or clicks from the NSF.
So yeah.
So like I made a list motivated by this question. Probably there's lots one can add there. I mean, like if you know what is interesting, if we at least approximately know what is interesting, we can improve algorithms that help us do mathematics, right? Because if the only criterion is that they generate things that are true, that's going to be very boring very quickly, right? So that could be the first bullet point. Maybe we can even use, this is much further off, but I mean, maybe we could use it to analyze difficult proofs, right? So if the proof is too big for a person to understand, then the person will kind of appreciate some software tools helping. And if the software tools have some notion of what humans find interesting in mathematics, that would could help. We talked actually a little bit about new ways of teaching and learning mathematics. Next point is more or less the same again. We talked about history of mathematics. Personally, I would be interested, for example, could we use this to distinguish like the classic distinction between pure and applied mathematics? Is there something in the data one can find that corresponds to that distinction, or is this distinction just purely historical and not related to anything actually inside mathematics? Right? Paradigm shift in mathematics. So Kuhn writes about normal science and then paradigm shifts. I think that could be an interesting topic to study. And yeah, and then everything we talked about was about like context. And I mean, everybody basically said this notion is context dependent. And so it depends on how we do mathematics and which groups of people do mathematics. And I think that could be also interesting topics to study, and maybe I mean, I'm sure lots of people are studying these topics, but maybe what I'm trying to say is that maybe these techniques, once they are developed, could kind of, I don't know, make a contribution to this. And probably there are many more points one could add. This is just something that we kind of collected this morning. Yeah, but definitely it's a very important question. Of course, you're right. Like if you don't have any idea of what to do with this question, why it would be just for data science nerds an interesting exercise. And I would obviously hope that it's more than that.
What I wanted to say about interesting in general, not specifically about mathematics, but is that this concept is a concept that is response dependent. is in the line of what Ivan was saying. It is something is interesting if it provokes some kind of response on some person. And this kind of response is going to be, for example, that you feel a certain emotion, or that you get triggered to do something, or so. This is the kind of concept that interests me.
Yeah.
So just by
it could still. So that means, I guess that's what you want to say, that it shouldn't be visible in the fossil record, but that doesn't mean that it doesn't leave traces in the fossil record that could be kind of recognizable. Like, I don't know, Jack Horner here at Chapman apparently argued that, and successfully, famously, that dinosaurs did childcare.
What?
Childcare. They were not like reptiles,
they
like
nurtured
not just
their young.
laying the eggs, but actually caring for their children.
Which is a very non-reptilian behavior. That was
So
the-
how
that
do
was
you
the
get
sort
that
of-
out of the fossil record? I have actually no idea, but
Oh,
apparently,
he found footprints going in and out of a nest.
Okay.
Like repeatedly coming back and forth, back and forth, back and forth.
Isn't it what birds do?
Yeah, and I think modern understanding is that dinosaurs are probably more descended from birds than reptiles. So
Precisely.
it kind of
That was part of the beginning of this paradigm shift of thinking of dinosaurs as reptiles versus dinosaurs as proto-birds,
Yeah.
right? This is one of these pieces of evidence that helps people
Yeah.
understand that.
Okay. Yeah.
Yeah. And he found it in Montana, by the way. He found this Myosaurus in Montana.
I talked to him a few weeks ago. He would be happy to take everybody up there digging. So if
I went
that's
this summer. It was great. You should.
if that's something you would like to experience,
Yes.
I regret that I didn't take this opportunity yet, but it's something I would like to do.
All right. Well,
Okay.
thanks for all the ideas. I think we should keep this conversation going and start working on the more concrete proposal that Marco was suggesting. Let's really think about this as a project. This was helpful as a brainstorming session, but I think now it's a good idea for us to be more concrete about it. So thank you for your time.
And thanks to Giuseppe, with whom
Yes.
we kind of started this conversation, and he's in Amsterdam.